Hi, everyone. Welcome. My name is Britta Forsberg. I'm the Executive Director for Save Barnegat Bay, and Avery Lentini.
Hi, everyone. I'm the Executive Assistant and Policy Advocate with Save Barnegat Bay.
Welcome to another workshop and a part of our series talking about MS4 or municipal stormwater permitting and stormwater requirements, which is a part of a grant funded through the New Jersey Department of Environmental Protection. And today we have a guest speaker with us from Rutgers, Dr. Chris Obropta, who's going to lead us through retention, basin, retrofitting, maintenance, and planning. So thank you, Chris, for joining us today.
Thank you.
We had hosted an in-person workshop with this content some time ago in Stafford Township, but for the benefit of folks who couldn't attend in person, we're re-recording this workshop for everyone to share.
Okay, so thanks. My name is Chris Obropta. I'm with the Rutgers Cooperative Extension Service. Steve Souza and I put these slides together. Talk a little bit about naturalizing detention basins, and it's a very popular topic right now in New Jersey, and hopefully we can provide some insight on this. Okay, so we're going to go through this really pretty quickly, but it should give you enough information where if this is something you want to move forward with, you'll be able to begin the planning process. Okay, so the first thing is we need to tame our stormwater runoff, and this becomes very important. We know that NOAA, the National Oceanic and Atmospheric Administration, calculated total damages from floods and hurricanes during 2021 to be more than $100 billion. So this is a serious issue. They also estimate sea level is going to rise 10 to 12 inches by 2050. But more importantly, what we see now is as climate continues to change, we're getting more intense storm events, and it really is putting a lot of stress on populated areas and increasing the risk of flooding and repeat flood damage. So there's a report here from NOAA that's referenced. You can look that up and take a look at that. If you have problems sleeping at night, you could read that, and it'll certainly keep you awake. Okay, here we go. It's not all about these extreme events, and everybody's got Ida fresh in their mind, but a lot of times we're planning for smaller events, more frequent events. A lot of these events, 1, 2, 3, even 4 inches of rain that occur can do a massive amount of flooding, but we can do a much better job of controlling them than we can of some of the hurricanes and the big nor'easters that we get. So the return frequency storms, the half-year storm, the 1-year storm, and the 2-year storm, those events don't mean they come once a year. Basically, the chance of getting a 2-year storm is 1 in 2 this year. So you're definitely going to get a 2-year storm, which is about 3.3 inches of rain over 24 hours. You usually get that every year. So these smaller storms increase the frequency of local flooding. So we often refer to localized flooding as nuisance flooding. It really does harmful environmental stress on our environment, because these are the storms that happen very frequently and carrying pollution to our waterways. And then also, because they're so frequently occurring, you do have these repeating ecological impacts, right? So it does a lot of damage to the ecology and the environment itself. So this is a little figure that Steve had put in here, and really just kind of focusing on this red area here where these smaller storms, about 90% of the time, you're getting these smaller storms. So, on the order of 2 to 4 inches is really what you're getting on a regular basis. Okay. And that's what we're really concerned about. The 100-year storm, the chance of getting that is usually 1 in 100. Because the data we're using is fairly old. The 100-year storm is calculated based on data that was collected before the year 2000. If you use the last 20 years of data, that rainfall total will actually go up about between 6 to 9%, depending where you are in New Jersey. So we actually really are designing right now for a 100-year storm that is less than what we're really seeing. So, okay, so here's some information about runoff. You've probably seen these figures many different ways. So natural conditions, a forested condition, we get about 10% runoff, about 50% infiltration. and we want to get water back in the ground. From a stormwater management standpoint, the best thing to do is to capture the water and let it soak back into the ground. It treats the water, cleans the water. It slows down the water from getting to the surface water bodies and helps reduce flooding, but improve water quality. During developed conditions, very downtown urban areas, we can get about 55% runoff and only about 15% infiltration. So the infiltration drops dramatically, and that's a huge problem. So we've actually altered this hydraulic cycle, the water cycle, in a way that because of our development, we've really changed how the water cycle behaves. And this is what one of the problems are when we start thinking about how to manage water with detention basins. So, okay, so as we increase development, we're increasing impervious cover. So impervious cover is any surface that water does not pass through. So it's the roof of a building, it's driveway to parking lot. With this increased impervious cover, we increase runoff volumes, right? Because more water is going to be running off of those hard surfaces because they don't have a chance to infiltrate into the ground. And it's going to be moving much faster because those surfaces are very smooth. You know, it's not like a vegetated system like woods or grass where water moves slowly through that. It moves quickly across pavement, quickly across rooftops. So it's accelerating the velocity of this runoff. Once it gets into the streams, it really alters the hydrology and the hydraulics of the stream. So the hydrology is really the watershed itself that drains to the stream, but the hydraulics of the stream itself. So what winds up happening is because the water is coming so quickly, the stream rises very quickly, fills its banks, and it often exceeds its banks. And that's when we start getting those flooding conditions occurring. It's carrying a lot more pollution with it because a lot of pollutants settle out of the atmosphere onto these hard surfaces and wash off. Plus, the water is moving so quickly over these surfaces that it is picking up a lot of that pollution, carrying it with it. Degrading water quality, you can see it on the bottom. EPA says about 70% of our nation waterways problems are because of stormwater runoff. So about 90% of New Jersey waterways are impaired, and the majority of the reason is because of stormwater runoff. So when I say impaired, I mean they're not meeting water quality standards for one parameter or another. We have loss of ecological services and functions, and of course, these harmful algal blooms that we see. They also refer to them as HABs. You see lakes being closed across New Jersey for recreational purposes because of these harmful algal blooms, and all of that is tied to stormwater runoff. Now, it doesn't take much development to increase the impervious cover to a percentage where we start seeing some water quality impairment of our waterways. Once we get beyond 10% impervious cover, our waterways start to become are really recognized as impaired. We can see impairments with as little as 2% of impervious cover. But you can see in this slide, half-acre lots to 1/8 of an acre lots really bring us into the high impervious cover range, and that's when we start seeing a lot of problems occurring. So it takes a little runoff can create a lot of problems. You can see some of these pictures here. The fellow in the lower left, you can see that severe stream bank erosion. You can see the muddy water on the right-hand side of the flooding that's occurring. And then, of course, the fellow waiting across the street trying to make his way to his house, away from his car, I guess. But these are all kind of common occurrences in New Jersey. So the problem with detention. So how do we manage stormwater? Well, we have these big detention basins, right? And these are how we've been managing stormwater since probably the late 1980s. Okay, so what happens is we quickly concentrate and move runoff from structures. So we push water away from the buildings. We push it downhill into a big centralized basin, and then we hold the water there and we let it out slowly over time. Okay, so it decreases the peak flow. So the water, because the water is getting captured there, it's not running off very quickly, it slows it down, but it doesn't really decrease the volume because those basins don't infiltrate a lot because most of them are very compacted, and it doesn't remove a lot of the sediment. So if it's not removing the total suspended solids, it's also not removing other pollutants that are important to causing water quality problems. Okay, now this is a very engineering geeky graph here that we use. And it's pretty easy to explain. If you look at the dark blue, this is pre-development. So this is the site before we put any houses on or anything, just a natural condition. So it rains, you know, a 24-hour storm, and at about 12 hours, you get about a peak here, peak flow, peak runoff flow. You know, and it looks like it's going up to maybe around 800 cubic feet per second, right? Now, the area under the curve, this blue area, represents a volume of water, right? So this shows you the peak of the water is about 800 cubic feet per second. The volume of water would be the area under this curve, okay? So now we put development in. Houses, roadways, we increase the impervious cover. So now we get a much faster runoff, right? Gets much higher. Okay, so here we're getting up to about 1325 as opposed to 800. And there's a lot more area here. So there's a lot more volume of water. So what we do is we put a detention basin in, right? And that detention basin will capture this purple area in this post-development and hold that water and let it out slowly. So you can see we can bring this peak down from about 1325 back down to about where it was before development, but we still have a lot more water. This light blue is much bigger than dark blue. So it's telling us that even though we've reduced the peak flow, we slowed the water down, we're releasing a lot more water over time. Okay. So this puts it in words. We reduce these systems do not reduce the runoff volume. They actually hold the water and let it out. So they don't really have any effect on volume. It really lets all the runoff from development that was coming off just go out over time. It does very little to recharge precipitation to let water soak back into the ground, and it does very little to remove pollutants. These basins remove some sediment will settle out, but if they did a good job of that, these basins would always be filled with sediment. We'd have to dredge them out, and they rarely are. So it captures some sediment. Sometimes that sediment washes out the next storm. A lot of it gets captured in these concrete low flow channels here that have to be cleaned out on a regular basis. So it really does very little for nutrients, and nutrients are what's important, the phosphorus and the nitrogen. That's what causes the algae to grow and causes problems in our waterways. Okay. So the conventional basin, there's no volume reduction because we compacted these soils when we built this. Very little water infiltrates these concrete low flow channels. You can see this one's buried in sediment here. They hurry water through the basin, so they don't really have any pollutant removal ability. They do increase regional flooding and channel instability. The reason for that is that we're releasing more water over time, and we're not holding it long enough. So if we go back to this basin, this figure here, you can see the original storm was pretty much done at about, I don't know, maybe 28 hours, you know, so the storm ended at 24 hours, about another 4 hours later, all the volume was gone, right? Here you can see it goes to maybe 35 hours. It doesn't hold it that much longer. So because we're not holding it that much longer and releasing more water, we are causing downstream flooding with these things. And then we also, they look ugly and they have very little ecological benefits. It's just turf grass. The only turf grass, the only thing that benefits from turf grass are Canada geese. And they actually add to the problem because when they defecate in the basin, that also washes out. So creating additional pollution in our waterways. So one question we have is, how do we get from what's on the left to what's on the right? You know, how do we naturalize these basins, turn them into more of a natural system that does a better job of treating water, holding water, infiltrating water, and really acts more like a natural condition that we would see in a natural water cycle. Okay, so we call that naturalization is what we call it, minimizing the modification of the existing basin, really kind of just going in and just planting it, and or not stop mowing it and just letting it go. And plants will grow. Those plants' roots will open up the pores in the ground, help for infiltration. Those plants will take up nutrients and filter out more pollution. So the basin will act in a very different way. The other thing we can do is we can go in and retrofit it, where we actually go in and we actually do modify the basin itself. So we may be pulling out the soil, we may be taking out the concrete low flow channel. There's a lot of different things we can do to retrofit, and we'll talk a little bit about that. So naturalization starts with the better design. So the problem here is that we already have about 700, and I think I calculated 787 detention basins in Ocean County alone. So these are existing basins. Okay. So that's a lot of places to start where you can go in and naturalize them or retrofit them so they can do better at improving water quality. Okay. Often stormwater management is an afterthought. We don't think about it up front. So when we're developing or redeveloping or putting retrofits in, we really need to think about how we're doing this and consider that up front. We don't always have to settle for end of pipe solutions. There's a lot of other practices out there like green infrastructure practices, and we use a lot of bioretention, also known as rain gardens, trying to capture water more near the source of where it lands, as opposed to letting it run down a hill, picking up all the pollution and going into a detention basin. So maybe we can capture some of that water in other places. And don't consider this innovative. This is not innovative. What we're doing is we're turning a grassed area back into a meadow area, which is a great thing for the environment, and it does a much better job of treating stormwater. It's really not that creative. It's something that we could be doing everywhere. And people talk about this as being these innovative solutions. They're really not. It's a pretty common way of dealing with stormwater. Okay. And then, whether you naturalize it or you retrofit it, you can certainly get better stormwater management results. Okay. So thinking about the proper design and community acceptance. So this is a big problem. If you have a detention basin that's in the middle of a development, surrounded by houses, that has been mowed for the last 25 years, if you go to naturalize it and let it go natural, you may get some pushback from the community. They may say, no, we like that mowed area. So there's often needs to be some community outreach before you start these things. A lot of times we'll go into a town and we'll work on a basin that's maybe not in the middle of a housing development, but on the edge of a housing development where it'll be a little bit easier to gain acceptance to naturalize the basin. Then we can use that one as an example to show other people so we can move on to some that are in more densely populated areas. Okay. So we always think about community acceptance when we're doing this work. The other thing about this is a lot of the public works people and a lot of the townships like this because now you're changing a basin that you're mowing once a week into something you mow maybe twice a year. So you've dramatically reduced the maintenance, right? So that could be a really nice thing. So thinking about this differently is really important, and trying to get the public engaged is really important too. So when we think about detention, the word detention means we're detaining water. Think about, when you were bad in middle school and you got detention, had to stay after school, they detained you for a couple hours and they let you go. Detention is the same thing. We hold the water for a period of time, we let it go, the basins go dry between storm events, right? Well, there's another term called bioretention. So retention is more of a term we think about of a wet pond where we retain the water forever. So a retention basin is always wet, always has standing water in it. When it rains, the stormwater comes in and it will increase the depth. So for example, the retention basin, also referred to as a wet pond, may have 3 feet of standing water in it all the time. And then when it rains, it may get 6 feet deep, and that extra 3 feet of water from the stormwater runoff will be stored on top. Over time, that extra 3 feet of water will slowly go away and discharge from the basin, and the retention basin will still have 3 feet of water. So it always retains the water. There's another term we've been using called bioretention. So once again, we're retaining the water, but in this case, we're retaining it in the soil. We're infiltrating it into the ground. And the word bio means life. So we have a system that has life in it, it's holding water. And really the whole idea is that we put in specialized soils that promote vegetation growth, promote infiltration, and we try to hold that water as long as possible and let it slowly soak into the ground. These basins are typically designed to hold the entire storm runoff from a storm event of up to a 2-year storm. So if you get 3.3 inches of rain, these basins are designed to hold that 3.3 inches of rain and never let any of it out, let it all infiltrate into the ground. Okay. Now you have to know that if we can hold that 2-year storm, we can capture about 90% of the rainfall from ever leaving the site. Okay. So bioretention, so you got vegetation, filters out the pollution, helps take up nutrients. There's a photosynthesis component, so transpiration of vegetation will pull moisture out of the soil and then transpire it back into the atmosphere, just like you and I perspire when we run. Well, water leaves our pores. The same thing happens with vegetation. It'll take up water from the ground and it'll be expelled through the leaves and then evaporated back into the atmosphere. So that's called evapotranspiration. The vegetation has deep roots, so it opens up the soil, so infiltration occurs, so it increases soil porosity, or the soil's ability to pass water from the surface to the groundwater table. And then the soil itself filters out pollution. Pollutants will attach to the soil. There's microbial activity in the soil that can decompose some of those pollutants, and that becomes another way of treating stormwater runoff. So it talks a little bit here about the soil. Soils are really the key component to this, right? Because the soils have to be able to infiltrate water, so there has to be some pores in the soil. So it can't be very compacted clay. It has to be a sandy silt loam where water can actually kind of pass through it. It'll hold the water, let it out slowly into the groundwater table. It'll remove the pollutants. It usually has a fairly high organic content, between 7 to 15%. Now we have to be careful with this. We don't want to add too much organic material, especially in the Barnegat Bay watershed, because a lot of the organic material has nitrogen in it, and nitrogen can pass right through the system into the groundwater table and eventually make its way from the groundwater into the bay. So we want to limit the amount of organic we have in there. So a lot of times we're on the lower end of that. We're more around 7% when we're doing systems in the Barnegat Bay. We also need some separation between the seasonal high water table. So SHWT is seasonal high water table. So what we do is we dig down and we figure out where that water table is. And we like to have at least 2 feet below the bottom of the infiltration system, the bioretention system, to that water table, so water can slowly seep into the ground. If we don't have 2 feet, we usually put an under drain in so we can take excess water away and discharge it later. After it's made its way through the soil, it gets treated and then gets taken away with an under drain. So storage volume, like I said, we try to capture as much rain as possible. Here, Steve is talking about the water quality storm. New Jersey has what's called a water quality design storm, which is 1.25 inches of rain over 2 hours. We're told by the state that 90% of the storm events come in less than 1.25 inches. So if you capture that first 1.25 inches, you can capture about 90% of the rainfall. The other storm he has here is 2.75 inches of rain over 24 hours. It's the 1-year storm. I was talking before about the 2-year storm, which is about 3.3 inches of rain over 24 hours. So these are all reasonable amounts of rainfall that you can capture in a bioretention basin, right? So the soil bed, usually it's about 85% sand, 15% compost. Sometimes it's as much as 92, 93% sand and 7% compost. So that's a way we mix that up. So the sand promotes infiltration. In a lot of cases in the Barnegat Bay watershed, the sand's already there. You may just have to amend it with some compost to help the plant material grow. Okay, the minimum 1 to 2 feet separation between the bottom of the bioretention system and the seasonal high water table. We talked about that. And then one of the most important things is we want this to drain within 72 hours. If we have standing water more than 72 hours, we're going to get mosquitoes breeding, and then a lot of people around the basin are going to be very mad. So we have to make sure that that water infiltrates quickly, gets into the ground, and after 72 hours, there's no standing water on the surface, okay? And this is the soil mix that we talk a little bit about here. This is a preferred organic content. Like I said, we see 3 to 7% is what's recommended. Sometimes it's 10 to 12%. So this is a mix that we typically use when we're amending the soil in a detention basin, trying to retrofit it to become a bioretention basin. And this is a cross section of it. It shows the soil, 6 inches of water ponding here, and that water will stay here. And once you get 7 inches of water, it'll go out this drain and go out. But 6 inches will sit in the bottom here until it has a chance to soak into the ground and infiltrate into the groundwater table. In this case, we've got an under drain system. So water is probably not getting into the ground fast enough here. So as water passes through the planting soil, it gets cleaner and cleaner. and gets to this underdrain. This underdrain will take it away, either deposit it right into the stream or maybe into the storm source system. But the theory is by the time the water gets to this pipe here, this underdrain pipe, it's clean. Okay, so we're discharging clean water. Plus, it takes a couple days to get there. So you're discharging clean water 1 or 2 days after the storm. So you're reducing the opportunity for flooding. Okay, so how do you plant this? A lot of different ways to plant this: seeds, plugs, just 1 gallon quart containers. There's a lot of different seed mixes out there that you can buy. Pinelands Nursery in Columbus, New Jersey has a great selection of seed mix. You can buy the Detention Basin seed mix and use that. We always use native plant material. We always source from local nurseries. We try to avoid any invasives, any exotic plants, just because they don't do well in this climate. Plus, the invasives tend to take over, and that becomes part of the problem. You need to be careful too. You make sure that the plants that the seeds that you're planting and the plants you're planting are right for the wetness of the basin, right? So typically these basins will go dry within 12 to 24 hours, so they're not wetland plants. So a lot of times they're a little bit less than wetland plants, so not obligate wetland plants, but maybe facultative plants. And we can see here you have some typical plants. So the river bulrush is an OBL, obligate wetland plant. This other Canada Burnet, another grass, is a facultative wetland plant. And then the bush clove, the other one that's circled, is a facultative upland. So these are different species, and it shows where they grow. There's lots of great stuff in the BMP manual that New Jersey DEP has about landscaping, recommending plants. But trying to match the plants to the wetness of the area they're going to be put in is really important. And plant diversity is important. You don't want a basin that's just filled with cattails or one type of sedge. You want to have some diversity, okay? So here we go. Some cases of naturalization. This is Clawson Park in East Amwell, New Jersey, a project that Princeton Hydro did and Steve did when he was with Princeton Hydro. 319H funding from New Jersey DEP. So New Jersey DEP gives out a few $1,000,000 every year through the 319H program. 319H is a section of the Clean Water Act that deals with non-point source pollution. So EPA gives DEP money and DEP grants it out to people who do projects like this. It's a great funding source to do naturalization or retrofit detention basins. DEP is very big into this. They like this idea. They become a big fan of it. And a lot of it's because of the work that Steve and I have done over the years doing this type of work. So about $125,000 they got. It's 2 waterways, Neshannock and Raritan drainage areas. Mostly Back Brook is the main waterway. The pollutants were nutrients, sediment, and fecal coliform, so pathogens, right? Historic frequent flooding, lack of stormwater management, and the objective is to retain the rainwater runoff, decrease nutrient loading, decrease nuisance flooding, and improve the aesthetics. So these are the 2 areas that we focused on, right? So you can see there's naturalize the basin there, create some rain gardens, create a stormwater meadow. And you can see this was the upper basin, okay? Not doing a very good job of draining, not very beautiful, not doing a wonderful job of removing pollution. Lots of flooding. These are pathways to the park. Nobody wants to walk on a park on that pathway. So this becomes a big issue. And then, of course, poor soils. This is in Hunterdon County. Not the greatest soils out there. So in this park, you could see a lot of clays, shale, and compacted soils. So what was done? The turf grass was stripped off. They loosened the compacted soils. They tilled it up. So a lot of times you can use the deep tillers. The other method is to dig and drop, where you go into the back corner with an excavator. You dig down 3 feet, pick up the soil and just drop it and work your way out of the basin, so you're not driving over places that you've uncompacted. And then you can see whenever you're working in a basin and adding good organic material, you're going to be using very small equipment because you don't want to compact it. So you can see a very small excavator here, a tractor here, just very lightweight equipment as not to compact it anymore. And this is kind of what it looks like ready for planting. And then you can see here's what it looks like afterwards. Very nice natural system. Has a nice mowed edge around it so people know it's meant to look like this. And that's one of the keys with retrofitting a basin or naturalizing a basin is keeping that clean mowed edge so people don't think you're just ignoring it. They understand that it's meant to look like that. Signage is also very important. And you can see you've got wildflowers growing in here, just a really nice area. Here's another basin. This is actually late winter following a major storm event. And then you can see how it gets naturalized over time, right? So these are things that we've been talking about, a very natural system. Here's some of the seed mix that was used. You can see purple coneflower is a big favorite of everybody's. Black-eyed Susie's, little blue stem. These are three of the. I mean, if you go any field in New Jersey, I guarantee you'll see a little blue stem just growing naturally, right? So these are some of the things that we see a lot of, and then you have some different fescues and things like that. There is an annual rye in here that they put in, so that comes up very quickly to stabilize the soil after they grade it. Then it dies away, and then the other things to come up the following year. Okay, so and then you can see here the conventional detention basin and then the renovated basin. And you can see 6 inches of water, right? So pretty nice. Okay. What about maintenance? So you need to make sure your staff is trained. So it's not routine mowing. There's always an operation maintenance manual whenever you do this, so people know what a weed is and what a weed isn't. You schedule maintenance, track maintenance, so you need to have good record keeping. So when someone's going to go out and mow the naturalized basin in late October, early November, or early spring, you're going to record it. You mowed it. You're going to record who mowed it, so we know the person who did it in case we have questions from them later on. So keeping those records are very important. Okay. Whenever we're going over the basin and mowing it, we want to use lightweight equipment. We want to mow high. We don't want to scalp the plants, right? Weed whacking, hand pulling, and spraying of invasives. So any invasive plants, we try to get out of there pretty quickly. Usually if you weed whack those to the ground, the other things will kind of grow over them and maybe shade them out. You might be okay. And you can see here some of the work being done here. Okay. This is going to be expensive. So Montgomery Township Shade Tree Commission in Pennsylvania. The first and second year basin maintenance is greater due to possible reseeding, plant establishment, weed removal, but then it drops significantly over time. So they estimated about $200, $300 a year to maintain a naturalized basin versus $2,500 to $3,000 a year for conventional basins. That's because you're mowing it once a week. It costs expensive to do that. New Jersey data shows the annual cost savings of about $4,000 a basin. And it's largely a function of the mowing. And it also frees up staff to do other things, right? So this becomes very important. And if you guys are mowing basins every week, there's other things that they can take care of in the town. That's very helpful since we usually lose a lot of our public works guys retire and often don't get replaced. So we're always shorthanded in that department. So here's another example, the Perkiomen Watershed Conservation, Lower Providence Township, naturalized 6 grass basins. Really started out by educating the public, remove the concrete low flow channels, remove the turf, planted with native trees, shrubs, perennials, wildflowers. Naturalizing 6 basins saved this township about $10,000 a year in maintenance costs. Okay. So in summary, properly managed stormwater causes environmental and ecological problems. We know that. I mean, we wouldn't be talking about this if we didn't know stormwater caused pollution in the Barnegat Bay, Tom's River, and the waterways that feed the bay. Things we're trying to protect, things we care about as residents in the Barnegat Bay watershed. And it's not just the major storms that are causing it. Everybody points to Ida and Floyd and Sandy, and yeah, those were big problems, but the everyday, 2 or 3 inch storm event can be detrimental to water quality. So we really need to focus on managing the smaller events. Um, Standard end of pipe detention techniques don't provide the correct solution. So these detention basins we've been building to capture the water at the bottom of the hill, all they do is to hold water and let it out slowly. They really do very little to reduce flooding. They do very little to improve water quality. They have very little ecological benefits. So these are things we know, we've accepted. Bioretention is the most commonly implemented green infrastructure technique. Why? Well, because it's cheap. It doesn't really, there's no concrete involved. Really, it's a lot of soil and plants and things that can be done fairly easily. And yeah, you need to be trained to do it, but you don't really need a high level of training where you have to run, some heavy equipment and pour a lot of concrete. So it becomes a really nice technique to use. It's well suited for these smaller storm events, highly scalable. We can build a bioretention system, which we often call a rain garden, that could be 100 square feet in size to treat runoff from a downspout on the house. We can also build one that's 2 acres in size to treat runoff from a development. So very easy to do and very good for retrofitting conventional basins. So we can really convert these traditional stormwater detention basins into bioretentions fairly easily. So naturalizing and renovating detention basins. So basins already are controlling the peak flow. So now we can renovate them and also reduce the volume, improve water quality, promote groundwater recharge. So there's so many more things we can do with it by simply changing it from detention to bioretention. Okay. And the function of plants and soil media really work together to yield the best results. You have to be very careful about making sure you have the right soil media, the right plants into place, so that you get the whole full benefit of this. So success with basin naturalization retrofit projects, a function of homework. So this is not something you just go out and do. You really need to understand the hydrology, the hydraulics, the environmental attributes of the site, the targeted basin. So there needs to be engineering associated with this. And often you need a landscape architect involved too to help pick out the plants and things like that. So a lot of times this is a multidisciplinary project. Sometimes you bring in ecologists to help out too. So there's a lot of different ways you can do this, but you really need to do your homework. You just go out and do it. Be careful with plant selection. Converting detention basins is often drier than expected. So a lot of times you're not using wetland plants. And this is true for bioretention. I mean, we use a few wetland plants, the blue flag iris, the cardinal flower. These are plants that are, even though they're wetland species, they do very well in bioretention because we've learned that over time. But a lot of wetland plants don't because it's just not wet enough, right? You have to always be careful whenever you're doing anything like this, not to compact the soil, and make sure you have the whole system is designed so you can facilitate maintenance, make sure you have access to it. So a lot of times you need to get in there and mow, and you have steep slopes. You have to be very careful on how you're going to get the mower in there to mow, even if you're only mowing, once a year, and if you're planting it, how are you going to get in there and make sure the outfall is clear and things like that. So just make sure you have access to maintenance and you have the maintenance manual. The most important thing about this is not overselling this to the public. Not being honest with them. It's going to look like a natural system. Some of you may think it's wild and messy. Some of you may love the way it looks, but it's not going to be a manicured, beautiful landscape that you might have in front of your house. It's going to be a very natural looking thing. So don't oversell it. Plant communities change over time. Sometimes we'll have small plants in there, and a lot of times birds will come in, they'll drop seeds. Next thing you know, you'll have oak trees growing there and things like that. And you actually can see how the whole basin can convert from a vegetated, naturalized basin into a meadow, maybe even to a forested basin. So there's a lot of things you can see as it grows over time and kind of regenerative on its own. And best to make deep-rooted, low-maintenance grasses the workhorse. So in other words, a lot of people love the beautiful flowers, but the warm season grasses that have those big roots that go down 3, 4, 5 feet are really crucial to making this whole thing work, and it's very easy to get established. And once they're established, they really do a great job. So that's the presentation. My name's Chris Obropta. Steve Souza and I put this together. A lot of this has done a lot of this work. Unfortunately, he couldn't be with us today. So if you have any questions or contact information, or you can reach out to the Save Barnegat Bay folks, and I'll be glad to put you in touch with us.